Welcome to the first video in a series of 4 about the unit circle. Here we'll talk about 16 points on the unit circle that we all need to be familiar with. What is the unit circle? Well, it's a circle whose radius is 1, whose center is at the origin on a graph. It turns out this circle has a circumference of 2 pi, and that number turns out to be important, as we'll see later. You may recall the general formula for circumference is 2 pi times the radius. If the radius is 1, then that's 2 pi times 1, or just 2 pi. Furthermore, the unit circle has an algebraic equation, x squared plus y squared equals 1. What does that mean? That means that any random point chosen on the unit circle satisfies that equation. I'll give you an example. This particular point happens to be -3/5, 4/5. If we take the equation of the unit circle and plug in -3/5 for x and 4/5 for y, we'll get a true statement. Here's what I mean by true statement. If you do the algebra and you work out the statement so that it's simplified, you get 25 over 25 equals 1. And of course, that's true. So that's what we mean by the equation of the unit circle is x squared plus y squared equals 1. The next basic concept associated with the unit circle is radians. What is a radian? Well, here's my unit circle. I've drawn it much larger so I can get a better view of it. This circle has a radius of 1. If I were to trace out an arc whose length was also exactly 1, then the angle associated with that arc would be exactly 1 radian. It turns out that a radian is approximately 57 degrees, but we don't need that number at this moment. This diagram here shows something interesting about how a radian angle relates to the circle. I've drawn in here 6 angles, each 1 radian in measure. The reason each of these angles is a radian is because each of these arc lengths is 1. But notice, 6 arc lengths around the perimeter, or 6 radians, doesn't quite make it the full way around the circle. The interesting question is, how big is this remaining piece? Well, remember, the circumference of a circle is 2 pi, meaning 2 times pi, or 2 times the decimal version of pi, if we wanted to think of it that way. And the distance around this circle is about 6.28. And that means that remaining piece is the decimal portion of that, about 0.28. Sometimes we say there are 2 pi radians in a circle, inspired by this picture. But we also like to think of there being 360 degrees in a circle. So in some sense, 360 degrees and 2 pi radians are the same thing. This is the same as saying 180 degrees and pi radians are the same thing. Let's examine some arcs on the unit circle. An arc is a portion of a circle, and an arc can be anywhere on the circle, different size and location. But we've built a tradition in math that when we talk about the unit circle, we only think of arcs of a specific kind. We think of arcs that start at this point. We call that the initial point of the arc, and it will always be the point 1, 0. It will always be the far right point on the unit circle. Why is that the point 1, 0? Let me take a moment to remind you just how small the unit circle is. Why do we draw it so large? So we can draw detail in it. So the initial point of any arc in the way that we think about and conceptualize the unit circle, the initial point is always 1, 0. Now, arcs generally go counterclockwise, and wherever they end, we call that the terminal point. I haven't done any math here. I've simply told you that all arcs on the unit circle in our consideration start at the point 1, 0. They go counterclockwise. There are exceptions for that later. And wherever that arc ends, we call that the terminal point. Now I'd like to look at a very special arc that's important to our study of the unit circle. Let's start at our initial point, like we always do. And let's consider the arc that goes exactly halfway around the unit circle and terminates here. This arc has a length of pi. This shouldn't be surprising. After all, the circumference of the entire unit circle is 2 pi. Therefore, the arc length of half the unit circle would be pi. Now, I want to focus on this point for just a moment. That point is typically referred to as the point pi, and we loosely say, here's where pi is on the unit circle. But let me remind you that that point isn't really pi. It's this arc length that terminates at that point that is actually pi. But we loosely say that's the point pi. What is that point actually in graphic terms? Well, it's the point -1, 0, isn't it? After all, let me remind you just how small the unit circle is. And you can see why that's the point -1, 0. So again, if we start an arc at our initial point, 1, 0, as we always do, go halfway around the circle, that arc length is pi. What if we were to go halfway around the top half of the unit circle? In other words, a quarter circle. Well, then wouldn't that arc length be half of pi? We could represent that as pi over 2. So again, starting at the initial point, if the top half of the unit circle has an arc length of pi, what if we went halfway through the first quadrant, or 1/4 of the way through the top half of the unit circle, or you could even express that as 1/8 of the entire unit circle? Well, wouldn't that distance be half of pi over 2, or 1/4 of pi? There are many ways to think about it, but we refer to this point as being pi over 4 when we actually mean the arc length that terminates at it is pi over 4. So again, with our initial point having the top half of the unit circle with an arc length of pi, what if we went 3/4 of the way through the top half of the unit circle? Wouldn't that terminal point then represent an arc whose length was 3/4 of pi? Think about it as 3/4 of the top half of the circle. So now we've identified 5 very important points on the unit circle. We call this pi, representing the length of the arc that terminates there. We call this point pi over 2, this point 1/4 of pi, or pi over 4, and this point 3/4 of pi, or 3 pi over 4. In fact, we could even call this point 0 as representing an arc whose length is 0, that both starts and terminates at that point. But let's express all these with a common denominator. Notice I've changed all the denominators of my fractions to fourths. This turns out to be a very valuable mental exercise, especially when you notice the pattern of the coefficients of pi. Because if we think of these as multiples of pi over 4, we can extend this beyond the first 2 quadrants to represent lengths of arcs that terminate here, here, and here. Following the same pattern and noticing the multiples of pi over 4 here, we could call this 5 pi over 4, this 6 pi over 4, and this 7 pi over 4. We could even label this 8 pi over 4, just to have the pattern continue. Now you'll notice some of these fractions are reducible. I put them all with a common denominator of 4 to show you a general trend, but let's now reduce all the fractions back to lowest terms and talk more about these very special points on the unit circle. Let's start by talking about this point here, which is thought of as both 0 and 2 pi. Well, 0 can be interpreted as the arc that starts and ends here, literally the arc of length 0. But 2 pi can be thought of as the arc that starts there and also terminates there after one revolution around the circle. In that sense, in a unit circle frame of mind, 0 and 2 pi are in some sense the same. Of course, 0 and 2 pi are definitely not the same number. 2 pi is about 6.28, and 0 isn't that. But while they're not equal, we like to say in trigonometric terms that 0 and 2 pi are coterminal. Definitely not the same number, but arcs of length 0 and 2 pi both terminate at the same point. Hence the word coterminal, or terminating in the same place. And before we go on, I'd like to examine one point here, just to remind you of something. Once again, when we call that the point 5 pi over 4, that isn't really the point 5 pi over 4. That point has x and y coordinates, which are decimals. But when we say that 5 pi over 4 is right there on the unit circle, I just want to remind you, that means that the arc that terminates there has a length of 5 pi over 4. Now it's worth noting that 5 pi over 4 literally means 5 times the number pi divided by 4. And if we put a decimal approximation for pi, I worked this out on a calculator, and I got about 3.9. So does that arc, you may see it as pink, does that arc actually have a length of about 3.9? Well, that makes sense. After all, we're in the unit circle. The unit circle has a radius of 1. So if the radius, you may see it in green, has a length of 1, then the solid arc in pink has a length of about 3.9. So that's logical. Think about it that way. So these are some very important points on the unit circle. And we'll come back to those in a few minutes. And now that we've seen 8 very important points on the unit circle, let's talk about degrees. Consider this arc here. As we discussed earlier, that arc has a length of pi over 4. Consider the angle at the center of the circle associated with that arc. So it turns out that angle is a 45-degree angle. It shouldn't be too surprising. But because that angle is 45 degrees, we say that the arc has a measure of 45 degrees. And because that arc has an initial point, where all of our arcs do, at 1, 0, and it terminates at pi over 4, we associate 45 degrees with pi over 4, and we essentially call them equal. Here's another example. Consider this arc. That arc is associated with a 90-degree angle at the center of the circle, and because the angle is 90 degrees, we call the arc 90 degrees, and we associate 90 degrees with pi over 2, because the arc terminates there, because pi over 2 is its length. One more quick example. Consider the arc of length 3 pi over 4. That's associated with a 135-degree angle at the center of the circle, and therefore we label the arc as a 135-degree arc, but we refer to this location on the unit circle as 135 degrees, again because the arc terminates at that point. And we can continue to go around the unit circle, hitting our 8 major points, at least the ones we've seen so far, by associating pi with 180 degrees, 5 pi over 4 with 225 degrees, and so on, and finally associating 2 pi with 360 degrees, or 1 complete revolution. Now I'd like to look at some more points on the unit circle of importance. A quick reminder first. Imagine an arc whose initial point is where all arcs start and goes halfway around the circle. As we've seen, that arc has a length of pi. Now imagine an arc 1/6 of that length, or pi over 6. Follow me on this mental journey. If we call the first point 0 to represent an arc length of 0, and the second point pi over 6 to represent an arc length of pi over 6, let's imagine what the multiples of pi over 6 would look like. There would be 6 of them in the top half of the circle, and 6 more of them in the bottom half. And furthermore, if we were to consider pi as 1 times pi, this would lead to an easy way to mark the terminal points of all the other arcs, because that arc would terminate there and have a length of 2 pi over 6. An arc length of 3 pi over 6 would terminate here, and you can see the pattern as we go. Now, having these all have a common denominator of 6 is very helpful to see the pattern in the multiples of pi over 6. But of course, mathematicians don't like things that aren't reduced, and some of the fractions that you see in front of you are reducible and simplifiable, so I'm going to simplify them all now into their more common forms. So what this does is it gives us many new points on the unit circle that we consider of importance and will be studying as trigonometry goes on. Now remember the multiples of pi over 4 that we spent a bit developing earlier in this video? Here they are again. If you combine the multiples of pi over 4, which we saw earlier, combined with the new multiples of pi over 6 that we just developed, and what you have here is a complete picture of 16 points. 16 points on the unit circle that we revere and figure are worth additional study. And these 16 points are a big portion of just about any trigonometry class. You'll recall that for the multiples of pi over 4, you may see them in green, that we associated with each one an angle in degrees. And we can do the same for all of these. And so what you see here, if you can see green, red, and black points, what you're seeing is this. The green points are multiples of pi over 4. The red points are multiples of pi over 6. And the 4 black points on the x and y axes, the so-called quadrantal angles, are both multiples of pi over 6 and pi over 4. And this picture that you see on your screen is a very important concept of understanding the unit circle as we go forward and study, in particular, these 16 points. Now would be a good time to remind you once again that the unit circle is actually quite small. It has only a radius of 1, but yet every time you see the unit circle, you'll see a giant picture that takes up the entire screen or page. But it's always worth keeping in mind that the unit circle is very small, but we don't draw it small because it would require us to fit in a tons of detail in a teeny amount of space, and that's just not something that's practical. But nonetheless, there are the 16 important points on the unit circle. Now let's take a look at something called coterminal angles. You heard this phrase earlier in the video. I'd like to delve a little bit more into it. So let's consider an arc starting at our usual initial point of 1, 0, and suppose this arc goes 2/3 of the way through the first quadrant. We've seen this arc before. It terminates here because an arc that terminates halfway through it is pi over 6, and this arc length would be 2 pi over 6, also known as pi over 3. That shouldn't seem new to you after what we just viewed, but we refer to that point as pi over 3 because the arc that terminates there has a length of pi over 3. So far, so good. Here's a question to ponder. Is that the only arc that terminates at that point? And it turns out the answer is no. Mathematicians long ago pondered the question, do arcs always have to go counterclockwise? Should those be the only kind of arc lengths that we allow? And it was a consensus at some point that we should allow arcs to go clockwise as well, such as this. And that arc that just appeared, you may see it as green, terminates in the same point as the red arc does, or the first arc, but it's going clockwise. Mathematicians decided that clockwise arcs, still starting at the initial point but going clockwise, should be considered as negative lengths. Now, of course, there's not really such thing as a negative length, but for the purpose of trigonometry, mathematicians have decided to call this the terminal point for negative pi over 6, negative 2 pi over 6, negative 3 pi over 6, and so on. And so it turns out, if you count your way around in sixths, the arc whose length is negative 10 pi over 6, also known as negative 5 pi over 3, terminates in the same place as the arc whose length is positive pi over 3. Because these two arcs, however different, do terminate at the same point, we call them coterminal. So, for any point on the unit circle, are there two arcs that terminate at that point? Actually, it turns out that there's infinitely many. Let me give you another arc that terminates at this point. Watch the graphic closely. Start by fixing your eyes on the initial point. Watch this. That arc went more than one full revolution, more than 2 pi radians around the circle. So if we consider this the terminal point for pi over 6, 2 pi over 6, 3 pi over 6, and count our way around, 6 pi over 6, also known as pi, 7 pi over 6, 8 pi over 6, and so on, when we get around to 12 pi over 6, or 2 pi, we're back at the initial point. But if we keep going, then we're at 13 pi over 6, and then 14 pi over 6. And again, mathematicians don't like to leave fractions unreduced, so I'm going to change 14/6 into 7/3. But what that proves, or shows, is that there's a third arc that terminates at that very same point. In fact, considering that you could go around the circle more than one full revolution, or even clockwise more than one full negative revolution, it's easy to convince yourself that there are infinitely many angles, arcs I should say, that terminate at that point. Now, we refer to that one point on the unit circle there as pi over 3 typically, sometimes negative 5 pi over 3, and sometimes 7 pi over 3, depending on what purposes the problem serves. The important point is for you to realize that these numbers are not equal just because their arcs are coterminal. I worked these numbers out on a calculator, approximately. They're definitely not equal, no surprise. So we're not saying the numbers are equal, but these three different numbers represent arc lengths that all terminate in the same place. And for our final consideration, Coterminal angles can also be expressed in degrees. Here's another example. This arc starts at the initial point, as always, terminates at a point that we could call in degree form 90 degrees. So there's our 90-degree arc. But that's not the only arc that terminates at that point. If I were to go clockwise, I could consider that second arc, you may see it as green, I could consider that as a negative angle. And it turns out that it would be considered a negative 270-degree arc. Negative because it's clockwise, and 270 degrees because, well, that's just what it works out to. 90 times 3 is where I got that. But those aren't the only two arcs that terminate at that point. Imagine we start at the initial point, watch the initial point carefully, and go more than one revolution around and still terminate at that point. Well, that was a counterclockwise angle, so that would be a positive. I worked out the arithmetic, and it worked out to be positive 450. It's worth noting here that an angle can go past 360 degrees in the consideration of trigonometric purposes in the unit circle. This just goes to show that there are 3 different angles that terminate there, and you could convince yourself, as before, there are actually infinitely many angles that would terminate at any given point. Well, we've now reached the midway point of this video, and we're going to change considerations drastically. Now that we've talked about 16 major points on the unit circle, we're going to try to locate the x and y coordinates of those points. We're going to start by looking at the coordinates of the so-called quadrantal angles, those that are multiples of pi over 4 and pi over 6. That also includes that they would be multiples of pi over 2. Then we're going to find the coordinates, the x and y coordinates of the other multiples of pi over 4. You see them here. And then we're going to conclude by finding the x and y coordinates of the other multiples of pi over 6. And then when we're done with all of that, we will have a complete picture of every coordinate point of every one of the 16 major points that we usually consider on the unit circle. It's worth reminding ourselves at this point, before we start, the unit circle is very small. And so these 16 points that we're finding all have coordinates between -1 and 1. And so we should expect a lot of decimal values. So we're going to start with the quadrantal angles. These are probably the easiest 4 points to find out of the 16 points on the unit circle that we consider valuable. Now remember, here's a more to scale version of the unit circle. So if I want to find the coordinates of this point, it would be the same as that point, as you can see in the bottom. But clearly that point is on the y-axis at +1. And therefore, that point is 0, 1. I can use that same logic again. Watch. If I want to find the bottom point on the unit circle, which would be here in our to scale diagram, then that point is on the y-axis and has a coordinate of -1. Therefore, it's the point 0, -1. And we could continue in the same fashion. This point is the same as this point, which you can convince yourself easily is 1, 0. And finally, this point is the same as this point, which of course would have to be -1, 0. If this isn't completely obvious to you, I recommend pausing the video or rewinding and convincing yourself. Well, now that we've found the 4 quadrantal points on the unit circle, in other words, where the unit circle intersects the x and y axes. Okay, so to find the next set of coordinates, the other multiples of pi over 4, we'll start with this one. If I want to find the x and y coordinates of that point, I have to find this distance and this distance. I don't know what those distances are. Well, just for algebraic purposes, why don't we call the first distance m? No reason I chose that letter, just a letter I could make an equation out of if I need to. But because pi over 4 is halfway through the arc of the first quadrant, then this distance here would have to be the same as the one on the bottom. We don't know what they are yet, but I could call them both the same letter, because in algebra that represents two different things being the same value. Now, in order to find m, one fact that I could exploit is that this point is on the unit circle, and by definition, the unit circle has a radius of 1. Therefore, this distance, which is a radius, is 1. And now that I see that I have a right triangle built inside of my picture, I'm going to use that to find the value of m. What I'm going to do is set up the Pythagorean theorem. You may know it as a squared plus b squared equals c squared. In this case, it's m squared plus m squared equals 1 squared. And watch now as I do some algebra to solve for m. 1 squared is 1. M squared plus m squared is 2m squared. And to solve for m, I decided to divide both sides by 2. To further solve for m, I decided to take the square root of both sides. Ordinarily, in an algebra sense, I would have a plus or minus radical 1/2 here, but m represents a distance, and I can discard the negative in that case. Now, square roots don't always distribute, but they do distribute to a fraction in that sense. We'll look at the numerator. The square root of 1 is 1. And now I've solved for m. Now it's worth noting at this point that in some courses, depending on your teacher or professor, you will not be allowed to have a radical in the denominator. And we'll have to do something called rationalize the denominator. Or in other courses, you wouldn't have to, and that would be a perfectly valid answer for m. It really gets teacher specific here. But if your teacher is the type who doesn't want a radical in a denominator, you would have to take that radical, 1 over radical 2, and multiply it by 1. I'm quite sure you've seen this trick before, but if not, watch this. By multiplying by a special version of 1, radical 2 over radical 2, I get an expression that can be simplified. Now notice, I still have a radical in my denominator, and wasn't my point to get the radical out of the denominator? Well, I'm just about to do that, because if you look at the denominator here, radical 4 is the whole number 2. And what this work on the right side of your screen shows, you may see it in blue, is that 1 over radical 2 simplifies to the same number as radical 2 over 2. Now, these may look like different fractions, but it turns out they are the same value. The second one does not have a radical in the denominator, and therefore is considered more of a proper way to express that. But let's not forget the bigger picture here. We were trying to find the coordinates of this, but that's good that I now know what m is. And knowing that m is radical 2 over 2, I now know the coordinates of the point I was looking for, and there they are. So now I've found the first of these particular 4 of our special 16 points on the unit circle. Well, now that I've found this one, the other 3 are very easy to find because they're just reflections. They have the same in xy coordinates, but because the other 3 points are in quadrant 2, 3, and 4, some of them will be negative, but they'll have the same value as the ones in quadrant 1. By the way, before I show you that, it's worth noting that radical 2 over 2, I worked it out on a calculator, is about 0.71, and 0.71 is less than 1. This is consistent with how small the unit circle is and the fact that we just found that point. And if you look at it in a more scaled version of itself, rather than the large picture at the top of the screen, looking at the bottom, I think it's easy to convince ourselves that that point at the tip of that arrow would have a decimal coordinate less than 1. So back to the point of the other 3 points being reflections of the first one. Here we can see that these 3 points would just have the same coordinate values except a negative x coordinate here, a negative x and y coordinate here in quadrant 3, and a negative y coordinate in quadrant 4. And that shows us what the 4 coordinates are of those other multiples of pi over 4. So finally, let's turn our attention to the hardest points to find, the other multiples of 6. And by that I mean the pi over 6, excuse me. By that I mean the multiples of pi over 6 that are not multiples of pi over 4. In order to find those, we'll start by finding this one. If I want to find the x and y coordinates of this point, I need to know this distance and that distance. Now again, in order to find them, I'm going to exploit the fact that this point is on the unit circle, which again by definition has a radius of 1. Therefore, this distance has to be 1. Now, unlike in the previous problem, the base and height of this triangle that you see are not the same value. So I can't call them both m. But I can exploit a fact that you may recall from a previous course. Watch this. This particular arc right here traverses 1/3 of the arc in the first quadrant. You may recall that pi over 6 is 1/3 of the way through the first quadrant. And because that's the case, this angle here ends up being 30 degrees. Well, because I have a right triangle, and you may recall the rule that the angles of a triangle add to 180, because I have a right triangle, I could do some arithmetic and discover that this angle here is 60 degrees. That will in fact make the angles add up to 180. And the reason I'm focusing on the angles here, which ultimately I don't want, I want the coordinates of the point. But the reason I'm focusing on the angles here is because there's a fact from many math classes ago that if you have a 30, 60, 90 right triangle, that whatever your hypotenuse is, it doesn't have to always be 1 like it is in this case, but whatever your hypotenuse is, the shorter leg, the one that's opposite of the 30-degree angle, will always be half the hypotenuse. This may seem very familiar to you, or it may seem like something you've never heard. So if you're hearing it for the first time, there it is. The leg opposite of the 30-degree angle in a right triangle is always half the hypotenuse, no matter what the hypotenuse is. That's just a fact. I'm going to use that fact in my particular triangle. So if this distance is 1, then this side, which is opposite the 30, must be half of the hypotenuse, which is half of 1, which is a half. And now I know the length of one of my 2 sides. But I still have a side length that I don't know here. So now I'm going to try to find the base of this triangle. Let's call it k. There's no particular reason I chose that letter. I just needed to pick a letter to make an equation out of. Well, once again, I can set up a Pythagorean equation here because I have a right triangle. Now watch as I do the algebra, enabling me to find k. 1/2 squared is 1/4. 1 squared is 1. Subtracting a fourth from both sides gives me this. Taking the radical of both sides gives me this. Again, I would normally put a plus or minus, except that k represents a positive distance, and therefore there's no reason to consider the negative root here. Again, square roots don't always distribute, but you can distribute them to a fraction as shown. And in the denominator here, radical 4 is 2. And what this algebra shows is I now know the value of k. But let's not forget, I was trying to find this point, and therefore, knowing that k is radical 3 over 2 tells me exactly what the coordinates of that point are. And here they are. So now I've found one of the other multiples of pi over 6. Let's move on to the next one. And it's worth noting here that once we find this one, that all the ones in the other quadrants will be mirror images of these and therefore almost instantly findable. But back to our second multiple of pi over 6, I don't have to show you the same algebra that we just went through there, because it turns out the same triangle inverted and rotated turns out to fit right there. In other words, I couldn't go through all the same work again, but the exact same logic would show me that this second point, which is 2/3 of the way through the first quadrant, has reversed coordinates of that. If you're not entirely convinced, hit pause, think it through. It shouldn't be too hard to convince yourself. And now I've found the coordinates of the two multiples of pi over 6 that lie in the first quadrant. So now what I'm going to do is consider the reflective properties of the quadrants. In other words, now that I know the coordinates of the multiples of pi over 6 that lie in quadrant 1, the other 6 of them are going to be those same numbers, with some of them being negative. But fundamentally, they're not going to change. So in quadrant 2, I'll have a negative x coordinate. In quadrant 3, I'll have negative x and y coordinates. And in quadrant 4, I'll have negative y coordinates. And now that I've found the coordinates of the multiples of pi over 6, let's consider the fact that we also found the coordinates of the multiples of pi over 4, and we had prior to that found the coordinates of the quadrantal angles, in other words, those that are multiples of both. So altogether, we now have all the coordinates of all 16 points that matter to us on the unit circle. And as we conclude here, it's worth noting that these are not the only 16 points on the unit circle. There are infinitely many points on the unit circle. But these are the 16 that we have to be able to have quick mental access to do problems in trigonometry, most of which get done without a calculator. So if you have a full command of these 16 points, and you know their radian measures, their degree measures, which aren't shown here, and their x and y coordinates, without almost any hesitation at all, you will be able to advance into a trigonometry course and have a very high probability of success. Without this unit circle, there are very few problems in a trigonometry class that you can do well. So I hope I've impressed upon you the importance of this lesson. Now, rather than memorizing them all, at the very minimum, you should memorize quadrant 1, because all the other points are going to be reflections of quadrant 1. In other words, just the same numbers with strategic negative signs inserted as appropriate depending on the quadrant. And that completes this lesson on the 16 most important points of the unit circle.